piezoelectric concept and especially the piezoelectric organic composites. Then I will move to present some experimental procedures, common experimental procedures, whatever in the processing techniques or related to the characterization of the formed nanofibers. Then I will move to share with you some challenges that a lot of researchers worldwide are facing related to this part, in addition to some updated solutions to overcome some of these challenges. Then I will present 3 examples about different applications related to piezoelectric nanofibers, and by the end I will give a brief summary, and by then I will be ready to receive any questions from you. So as an introduction, the piezoelectric mechanism is mainly related to the transducing efficiency from the mechanical energy to electrical energy. This mechanical energy could be in different forms, including mechanical vibrations, stresses or pressures, even bending and tension stresses could be converted using the piezoelectric mechanism into electric energy. This technique is widely used in the concept of energy harvesting, and especially the mechanical energy harvesting applications, depending on the actuating mechanism related to the mechanical initial exposed mechanical excitation, and the usage of such piezoelectric mechanism is widely involved in different applications, including biomedical sensors, wearable electronics, smart textile, vibrational detection, industrial applications, different applications, and I will go further to introduce some of these applications. In addition that, the excited mechanical energy could be in different forms, even to include the sound acoustic waves. Yes, it could be also detected or harvested using piezoelectric membranes, and this one specifically is becomes a recent interesting point of research in different fields, not only in energy harvesting or acoustic energy harvesting, but also for industrial manufacturing and healthcare or health monitoring. So moving to a brief theoretical background about the piezoelectric membranes. Firstly, there are different materials, whatever inorganic or organic materials, which could access or which could accept the mechanical excitations and convert it into electrical energy form. But in our talk today, I will focus on the organic materials, and one of the most famous organic material in this field, which is polyvinylidene fluoride, PVDF, which has an advantage compared to a lot of other organic materials according to its unique piezoelectric properties, even without quite complicated procedures of fabrication. You do not need initially to make stretching or pulling or electric pulling treatment. For example, the material itself could accept the concept of piezoelectric or to convert quite low mechanical energy into the form of electrical form. So not also this advantage in the PVDF, but also it has some useful properties even compared to the inorganic materials, such as its lightweight, flexibility to be used in different applications, especially the smart textile and the wearable electronics, and also it could be formed in a relatively high purity. It has relatively excellent resistance to different acidic or basic or base solvents, in addition to its higher stability according to applied high electric field. But to be honest with you, the PVDF or different organic materials are definitely lower in piezo response compared to some inorganic materials, for example, like the PZT, which is used in wide applications commercially. However, as I said, the organic materials, it's like a matter of trade-off. The organic materials have some other advantages compared to this point of the piezo response. In addition, PVDF could be developed to produce relatively large voltages with quite lower forces. It could be sensitive to detect in some applications a fraction of Newton in range of millinewton, and within this range of very small forces, it could generate in some applications up to more than 10 volt, for example. So this development in the material makes it promising in different energy harvesting applications. And the main concept of this PVDF, or generally any piezoelectric material, that the polar crystalline nature of the material, which is considered the main reason of the superior, relatively superior piezoelectric performance compared to other organic materials. So let's move more related to the polar nature of the material and how it could be affected by external mechanical pressure. So PVDF itself includes, inside its crystalline structure, it includes electric dipoles, positive and negative. They are quite correlated to each other by its nature, and these dipoles could be responsive to applied mechanical stresses, and consequently these positive and negative could be reoriented to make one side of the material, as you can see here from this simple figure, by applying a mechanical pressure. These dipoles could be reoriented in a certain direction so that the majority of positive to be in one side, the majority of negative to be in the other side. Quite similar to capacitor. It's not a capacitor, but quite similar to the capacitor concept, and consequently we can generate voltage from this applied pressure. PVDF could be formed in different forms, as we will discuss later. It could be formed in thin film form or cast film. Even its original nature is in powder form or pellets form. However, over the last 2 decades, a lot of research work are correlated to the generation of PVDF microfibers or nanofibers through different techniques. One of them is the most famous technique, which is the electro spinning. Because of the nanofibers generally, or microfibers, whatever microfiber or nanofiber, could have a better chance to make a better reorientation for the included dipoles, and consequently it could be more effective compared to the case of thin film or the powder form. In addition, we should know, all of us, the main advantage of going to nanostructures to have better surface to volume ratio, and consequently most of your properties could be enhanced compared to the bulk form. However, the traditional techniques of generating piezoelectric nanofibers or polymers from PVDF, sometimes it can have some drawbacks of lack of mechanical stretching. The stress strain curve is very short. The breaking strain in some cases could be less than 5% elongation. So these are some drawbacks that we will see later how to overcome such disadvantages. Moving in a deeper way to the what's found inside the PVDF organic piezoelectric material. So the molecular structure here of the PVDF, as shown here in this slide, it's consisting of repeated monomer units CH2 and CF2 as shown in the left diagram. Okay, and the crystallinity of this organic material is quite good compared to different organic materials, because a lot of organic materials could be suffering from the amorphous nature of crystallinity. However, for this one or for this type of material, it could reach up to 50% of crystalline structure compared to the surrounding amorphous domain of the material. And this material has a relatively low melting point. It differs according to the structure of PVDF and the size of nanofibers, impurity, and so on. In most of applications or most of research literature, it has a melting point in between 160 to around 180 degrees Celsius. In some applications, it could be considered advantage, but in some applications, it could be quite restriction for using this PVDF. Let's move in a more deeper way inside the crystalline structure, that based on the chain conformation of the order of these polymer chains, the PVDF could be found in different phases according to the right diagram. If you can see that the chains of CF2, sorry, CF2 or CH2 could have different forms as seen here, alpha phase or beta phase or gamma phase, depending on the nature of the material itself. Is it powder? Is it thin film? Is it nanofiber? What is the treatment that you are going to use? Here we have to mention from the beginning that the main phase that we need for energy harvesting applications will be the beta phase, the middle one, because this beta phase is the best from the perspective of the piezoelectricity, because this phase has majority of dipoles or oriented dipoles. So the upper side, for example, could have majority of positive. The downside could have the majority of negative, or vice versa, depending on where is the fluorine, where is the hydrogen. But in this case, it's more dipole oriented compared to other phases, such as alpha phase and gamma phase and also beta phase. So again, we will focus later in the upcoming slides about this beta phase and how to calculate this one, because it's a matter to prove whether your material is more piezoelectric or less piezoelectric. So as I said, that the piezoelectricity of PVDF nanofibers has been strongly introduced in the recent research over the last 2 decades for its different wide of applications. So let's move to another point related to the experimental procedure. And here we will divide or split this experimental procedure into 2 categories. The first category, how to fabricate the nanofibers of PVDF. As we said, that the nanofibers is more effective compared to other forms for higher beta sheets, higher piezoelectric efficiency, and depending also on the higher surface to volume ratio. So that would be one category, and another category related to the procedures of the characterization itself of such nanofibers. So here I will move to the techniques of fabrication. Of course, the most convenient one is related to the electrospinning, as shown here. For whom of you didn't know or hear about the electrospinning, it depends on applying high electric field or high electric potential within relatively smaller distance between 2 points, the transmitter or the syringe needle, which will contain the organic solution, and then it would be pressed by or it would be pushed by a syringe pump, and then the high electric field will perturb or make perturbation for the generated jet of the solution, and then it would make what's called by Taylor cone, and then over this distance, when it reaches through a metallic collector side, it would be solidified in the form of nanofibers, depending, of course, on the, different parameters such as the viscosity of the solution, the value of the electric field, the feeding rate or the pushing rate of the solution. You can control your formed nanofiber. So the principle of the electrospinning is the stretching of the polymer in a uniaxial direction, depending on, as I said, the viscosity of the solution, and under applying electrostatic force coming from the highly exposed electric field. Then there would be a continuous set of nanofibers could be generated, hopefully without disruption, given an enough solution to feed, or we can have some troubles with this nanofibers, including the formation of beads, for example, or discontinuity in the formation of nanofibers. Then the DC voltage, DC high voltage, could help to subtract or to withdraw the jet of the nanofiber coming from a precision bump, and then the formed nanofibers could be received on a metallic collector as shown here, or this metallic collector in some applications could be replaced by high-speed rotatory drum. The difference between both, as shown here with the simple SEM images as examples, that whenever you are generating the nanofibers on normal metallic collector, or even a drum but with a relatively low speed rotation, then you will have random oriented nanofibers as shown in the left SEM. However, for the right SEM, here you can see mostly aligned nanofibers. It could be generated by different techniques, but one famous technique is to use high-speed drum with a speed minimum to be 3,000 or 3,500 RPM. Most likely, the formed nanofibers would be quite aligned, and it depends on the application that you will apply. Here, the diameter of such nanofibers in different literature, most likely it will not be less than 70 nanometer, and it's open range up to micron scale. There are other techniques as well compared to the electrospinning, which could be helpful in the formation of quite larger scale generated nanofibers, because one of the most bad disadvantages of the electrospinning technique, whatever in PVDF formation or in other polymers, is related to the relatively low scale of the generated nanofiber mats. So there are other techniques, for example, like the needleless electrospinning. So it's like a modification of the one traditional needle setup, so that you can reduce the repulsive interaction according to Coulomb force, and consequently you may add different nozzles of ejecting the nanofibers, and consequently you may have a higher capability of the scaling up. One of the most famous commercial examples is like NanoSpider from El Marco company in Czech Republic. This is one famous example about this technique. There are other techniques to generate nanofibers like PVDF nanofibers, does not depend on which do not depend on the electric field. Like the first photo here related to solution blown spinning, which depends on the relatively high pressure of air blowing, which could affect on the polymer jet, and consequently it can form nanofibers, but with replacing the traditional contribution of the electric field. This technique is more convenient compared to the electrospinning because of the opportunity of higher scaling up. However, it has some drawbacks, such as special nozzle design. You need most likely you will need to redesign the used nozzle according to the used polymer or the used organic solvent, in addition to the trade-off between mechanical pulling and electric pulling, because in this case, for example, and in some piezoelectric nanofibers, the electric field would be much more effective in reorientation of electric dipoles and consequently enhancing the piezoelectric efficiency compared to the mechanical effect of the air pressure. So each technique, as I'm saying, has some pros and cons depending on your choice. There is one last example here about fabrication techniques related to melt-blown spinning. This one is traditional in fabrication of face masks because of its high scaling up opportunities compared to the previous techniques. However, it has some drawbacks in the formation of nanofibers from the microfiber level, because most likely this technique is forming firstly microfiber, and then by the time it could be converted into nanofibers. So in the case of generation of nanofibers, it's relatively lower used compared to the solution blowing and electrospinning within the PVDF nanofibers. But if you would like to fabricate PVDF microfibers or PVDF cast film, in this case, the melt-blown spinning could be your optimum choice. Then I will move to the second category of the experimental procedures related to the characterization itself, how to characterize the PVDF nanofibers and to know initially, without making piezoelectric analysis, that you are expecting that this nanofibers would have piezoelectric performance. So let's start with the first one related to X-ray diffraction. As shown here, that it depends on the peaks of the pattern of the diffracted X-ray and depend on the angles of diffraction. For example, there are some angles like what's shown here. It's related to both powder and casted film. And these angles or these peaks are more related to the conformation of alpha phase, which is called trans-gauge conformation. And this conformation of the bonding between, it's a matter of orientation of the atoms inside this organic solvent, but this structure is mostly non-polar. Okay, so in this case we will have anti-parallel arrangement of the chains, and consequently we will have a very weak piezoelectric performance within these peaks. However, if you prepare the PVDF using electrospinning or solution blown spinning, then most likely you will find that the previously shown patterns or peaks of patterns related to alpha phase, most likely it start to be disappeared, and other peaks related to the beta crystalline phase would be relatively shown, which is related to all trans formation of the monomer chains, and consequently this one, which is called beta phase, is the most used one or the most needed one to form the piezoelectric nanofibers according to the orientation of the dipole moment parallel to each other, and then it would be highly responsive to any applied forces on the PVDF nanofiber. And if you'd like to calculate the beta phase contents. This is a simple equation to compare between the area under the curve of X-ray diffraction between beta phase planes or beta phase peaks and alpha peaks. Whenever you have more percentage up to 100%, then you have more beta sheets, and consequently your material will be more piezoelectric. Okay, in literature, the maximum one could reach, to the best of my knowledge, not to exceed 90% in some cases, which has majority of beta phase. Related to another technique, and in some cases you may choose one of both, not necessary to use both techniques, XRD and FTIR spectroscopy. Again, for FTIR spectroscopy, the peaks of whatever alpha or beta phases could be shown as a pattern of peaks here according to the vibration of the internal bonds inside the polymer. And consequently, you can calculate the ratio between the peaks of beta phase, between the peaks of alpha phase, but this time you are depending on the intensity of the transmittance, not the area under the curve. And in this case, you can calculate the fraction of beta sheets formed in the material. And as I said, it's highly preferred to have the highest possible beta phase. It will not reach 100%. Most likely it would be here in range between 80% to 90%, so that you can have quite superior piezoelectric nanofibers. Other parameters that we may use, and it's very important to measure the piezoelectricity of the material, which are D coefficient and G coefficient. D coefficient, which means simply the formed charge compared to the applied stress or the applied force, and it would be in the units, main unit of Coulomb per Newton. But here for 1 Newton, we are expecting very relatively small charges. So most likely it would be in range of pico-coulomb per Newton for most of PVDF nanostructures or nanofibers. Here, this D is a tensor, or it has a matrix related to the direction of the applied force and the generated voltage or generated charge. Then we have the most famous or most convenient two parameters is D31 and D33, which means that you are applying, for example, XYZ, for example, simply, you are applying the mechanical excitation in the direction of X, for example, or horizontal, to be like stretching, for example, or compression, or to press on the material by a pressure in the direction of Z. So X, for example, could be noted to 1, Z to be noted to 3, for example. And in both cases, the dipoles would be in the direction of the thickness. So it would be the third degree of freedom, or it would be considered D31 or D33. So the first subscript is related to the dimension of the generated charge, and the right one, or the second one, which is here 1 or 3, is related to the direction of the applied mechanical excitation. It depends, of course. Each D is depend on different other material dependent parameters, including the electromechanical coupling coefficient, the dielectric constant, and the elastic compliance, or the effect, the mechanical effect, and it's preferred to calculate it at a constant electric field. Here, the most important one, or the most used parameter to check if the piezoelectric, if the material has high piezoelectric or lower piezoelectric performance, is the one of D33. Okay, and I'm giving you here one example about some machines to measure D33 or D31 in a straightforward way. You can make your own handmade setup, or you can purchase one ready made facility, for example, like this one, D33 meter from an American company called APC. There is another coefficient which is G. I will not talk about this in more details. It's related to the developed electric field compared to the applied mechanical stress. It has the same nearly concept of the previous D coefficient, but here I'm correlating it, or I'm trying to remove the effect of the dielectric constant of the material, but it would have the same notation G33 corresponding to D33 according to the Z-axis of both mechanical excitation and electric generation, or D31 the inserted stretching, for example, in X, and then you can have charges or field in the Z direction. Moving to a very important part related to the piezo analysis itself, how to detect the generated voltage from applied mechanical pressure or forces. So here, there are different analyses. The most important one is to detect the generated voltage versus time at different applied mechanical excitations. Whatever, you can apply falling masses, for example, on the nanofiber mat. You can apply cyclic force or cyclic pressure. You can apply bending at different angles for the material or for your membrane. You can start stretching or making tension on your material or your membrane, and then you can see the generated voltage versus time. So here there are different factors within these aforementioned different mechanical excitations, including the amplitude of your mechanical excitation, the cyclic frequency that you are using, and also is it impulse or not. For example, like falling mass. Falling mass is only single effect, and it would be like impulse effect, mechanical impulse effect, to check the generated voltage from your membrane. Then the nanofibers here, for example, on this photo, for example, this is like an example to the setup that we are using here in Kuwait. The nanofiber mat is tested under different cyclic loads, and the sample, I'm adding it as a sandwich between two sheets of foil, and I'm trying to remove air as much as I can, and then connect it to two shielded wires. This is very important to reduce any coupled noise within your measurement, and also you need to use high impedance oscilloscope, or in some cases to use high impedance amplifier firstly before going to showing your signal, your generated signal on the oscilloscope. Okay, there are other measurements, such as you can measure short circuit current versus time under different mechanical effect, and also you can calculate the power density that your material could be generated, and this is very important from the viewpoint of the power electricians, to know the power density per certain time, for example, like kilowatt hour, and to manage the calculation of cost, and then they can check how effective is your membrane compared to other techniques of energy harvesting, or other membranes or other facilities of energy harvesting units. Also, in some literature, they are measuring what's happening inside the material at different electric field. We call it polarization field hysteresis. It could be measured using some facilities, but here I'm introducing one example to a simple circuit. It's called Tower-Sawyer circuit, so that you can measure the polarization field hysteresis loop of your material. Here I'm presenting some examples to the obtained results from piezoelectric. You can measure, let's start from the top left corner one, and then moving to the right. So I can measure the voltage versus time at different cyclic applied force, at different amplitudes also of force or pressure, then I can control the frequency of the cycling so that I can measure the voltage versus force or pressure at constant frequency. Then I can measure using the same aforementioned setup. I can measure the current density per cyclic force or pressure, and from both within full wave rectifier, I can measure the generated power density. The second row shows other measurements, for example, like voltage per falling masses, which is called impulse loading, or to generate force from the bending of your material. In some cases, we are putting the material or membrane on our toes or fingers, and then we can check the effect of twisting on the generated voltage. And also we can do it in elbow or any joints like knee and so on. And this is one of the recent applications of energy harvesting from athletes, for example, or to monitor the health of patients, for example, after surgery, according to their ability to move their joints. Some challenges that the people are facing currently related to this part. For example, as I said before, that the PVDF or any organic piezoelectric nanofibers could have relatively slower or smaller response in voltage compared to other inorganic materials. So in this case, there are some recent solutions to use some additives which could help in the more reorientation or more alignment of the oriented dipoles inside PVDF. The most famous one is to add zinc oxide nanoparticles, and here you can see on the top of top image here or top curve here that you can see that by increasing zinc oxide up to certain limit, then you can increase the generated piezoelectric voltage. Also, one very famous challenge for the PVDF nanofibers, that it's brittle. It cannot withstand different mechanical excitations, especially the stretching one. Most likely the elastic strain level or even the breaking strain level could be in most of cases not exceed 5 or 6%. So this is a very tough range for different industrial applications. So in this case, we have to think about some additives, for example, like polyurethane or nylon, so that you can increase the stretching capability or to increase the breaking point of the strain. However, as you know, that here we will have a trade-off. So you are adding another additive, then you are expecting that you are losing the main material of PVDF. So you are expecting that you will have a lower piezo response. However, and this is like an innovative concept in the last year, and our group has a good contribution in that, and we published recently a paper in Scientific Reports related to that, that we can add the polyurethane, for example, up to a certain limit, up to 15%. So we are losing 15% of the initial PVDF, but in the same time, we are increasing the generated voltage, as you can see here from these two graphs, that adding TPU or thermoplastic polyurethane increases in a very clear way the breaking strain. In some cases exceeds 90%, but it's also could increase the generated voltage from the material. And this is some innovative concept that some people are, or some research groups worldwide are working on over the last 2 years. So here, the idea is to depend on the better stretching of the carbon chain backbone inside the monomer chains, so that it could affect as a stretching for this backbone, and consequently you are increasing the distance between the positive and negative, or consequently you are increasing the dipole moments, and consequently you will have a better piezo response. Also, other challenges, as I said before, related to the scaling up challenge in the process. Now, most of the people are starting to work in other techniques, such as the solution blowing technique or electro-aerospinning, to try to integrate between the electrospinning concept and the solution blowing concept also. Another technique related to all what I said, it could be considered pre-treatment techniques, but there are other techniques related to post-treatment or post-control, that whenever you have ready-made PVDF nanofibers, you made it already, okay? But you can control the dipoles and increase the dipoles using different strategies, such as annealing. There are some literature are talking about annealing up to 100 or 120 degrees. It could enhance the orientation of the piezoelectric once it becomes dried. Also, the stretching itself, if you can stretch the PVDF, then you are stretching the carbon backbone chains, and consequently you can increase the dipole moments, as I said, between the fluorine and the hydrogen, or from the positive and negative dipoles, and consequently you may have a higher piezoelectric response. However, and to be honest also, here there is another challenge of the reversibility, the possibility to have a reversible process. So for example, if you annealed a sample, or if you stretch the sample, and then you would like to return back to the original state, in most of the cases, it would be irreversible process. Then I will express in the remaining few minutes, I will express quickly the three examples as applications for the piezoelectric nanofibers. The first one, as we said before, the mechanical energy harvesting. Mechanical energy harvesting could be used extensively within the applications of wearable electronics or smart textile, which is helpful in motion harvesting or motion detection, health monitoring, as I just said a few slides ago, that you can control or evaluate the motion of any patient within a hospital, the motion of its joints, its fingers, and so on, especially after surgeries. Not only to this limit, but also you can use your nanofibers in breathing sensor, depending on the generated voltage from the flow of your breath. Also, it could be used also in cough monitoring. And this is like a technique and measurements that have been used in PVDF nanofibers journal papers in the last 10 years. They are putting some nanofiber membrane on their neck and try to have different cuffs, and then to check the voltage. And by other integrated disciplines such as IoT or machine learning, you can have like an estimate about the status of your patient. Also, it's used within some industrial applications, such as detection of low frequency vibrations, as shown in the below two left figures, that in some cases you can control, or you can check the quality of some strings within textile manufacturing, for example, or you can check the stability of some devices, for example, the stability of fans, for example, if it's stable or not, depending on if it's not stable, so it will generate higher vibration, and consequently you can generate more voltage, which indicates that that there is something wrong in the stability or the position of your tool that you are adding within a certain machine. Another important application related also to the mechanical energy harvesting related to the footstep generation. Footstep generation means that you can add within your shoes, you can add some nodes of piezoelectric material, and it could be used to self-powered turning on of other sensors, for example, or you can use it within a charging of in units. So you are trying to harvest energy from yourself, from your running, for example, so that you can generate some voltage. Also, the footstep generation could be helpful within cheap lighting. So, for example, it's used, this technique is used in some buildings, especially in Europe, that whenever you have some crowdness in a certain building, so the floor, down to the floor, you will have some piezoelectric nodes, and then the lighting will be turning on, okay? But if there are no crowdness, then the lighting will be quite dimmed. So it could be considered cheap and smart lighting also. In addition, it could be used within smart traffic. This technique has been used in some European countries to control, to offer automated control of the traffic signals, and also to be combined with machine learning and other computational subjects, so that you can estimate the best routes for transportations and so on. Our group have some work in that, and we recently published one paper related to our solution blown spinning PVDF to be efficient sensing nodes for footstep generation. One last application related to the acoustic signals detection. Here I'm showing here a certain, a very simplified setup used to detect acoustic signals, or to convert the acoustic signal, which could be considered mechanical excitations in all cases, or mechanical waves, to be transduced by PVDF nanofibers membrane into the form of electric voltage. So it can be used in energy harvesting or detection, but not only to this limit. It could be considered in some acoustic communication, especially if it could be developed underwater, for example, so that we had some work, our group had some work previously related to the signal retracing. So, for example, we were adding different frequencies of acoustic signals with different amplitudes on PVDF nanofibers, and we found that some audible frequencies could be retraced with minimum distortion of the signal, and with generated frequency or output frequency much similar to the input frequency with minimum error. In worst case, it was around 1% frequency error. This publication was published in the Sensors journal in 2020 related to acoustic signal detection and retracing. Not far from these applications related to the self-cleaning filters, the PVDF could be used in some cleaning for water, or between the solutions, depending on the static charges on PVDF and the generated electric field that you can generate from mechanical excitations. So you can make removal of oil using these PVDF membranes, but in some cases it's highly preferred to add more catalytic structures within the PVDF nanofiber, so that it can enhance the efficiency of such filters, such as added titanium oxide nanoparticles. Then in another way, it could be used depending on the static charges in removing or acting as antibacterial effect, or to try to kill or to make some bacteria to be inactive or less in count compared to the original case without generating electric field from the PVDF. And also there are some recent reports, you know, COVID-19 pandemic and its problems. There are some reports talking about the effect of static charges of the PVDF on the protein shell of the COVID virus itself. Here I'm showing some images related to the atomic force microscope based on the piezo force microscope mode, which shows that the PVDF nanofibers could accept the reversible process. What does it mean? It means that PVDF is not only transducing mechanical excitations to electric voltage, but it could make the opposite. Okay, it could make the generated, it could transduce the applied voltage into some mechanical roughness disturbance or mechanical energy. And this mechanical disturbance of the surface could affect also in the self-cleaning trials. So here, this is one example of the self-cleaning filters. One question was mentioned in the chat box related to the piezoelectricity, a clean source of renewable and of renewable energy. The answer is yes, related to the energy harvesting concept itself. It's of course it's a clean source of energy, renewable energy. However, there is some trade-off about the material itself, because some scientists could consider that PVDF is not the best biocompatible material, so that it cannot be considered the clean 100%. So there are some other work related to more biocompatible materials, for example, polylactic acid, for example, but the piezo response is quite smaller or much smaller compared to the normal PVDF. So the answer is yes, related to the renewable energy concept. Come on, you are transducing mechanical energy to electric energy, and both sides are clean. But the material, the intermediate between both resources of energy have, in some cases, some concerns about its biocompatibility. So let's move to the final slide about summary about the presentation. And thanks a lot for your attention. And I hope that I was not like a boring presenter for you. So as a summary, we talked about the piezoelectric membranes. It's a concept to transduce different mechanical excitations into electrical energy. One most promising and famous example about that related to the PVDF nanofibers, which is one, as I said, which could have the advantage of the alignment of beta sheets or alignment of dipoles compared to other phases like alpha or gamma phases. There are some different additives and processes that can enhance the PVDF nanofibers performance, and it could be used in different applications related to energy harvesting, wearable electronics, filters, and possibly it has different promising applications for the future, as I said, to be integrated with IoT or cyber physical systems or machine learning and cybersecurity as well. So coming back to your questions, okay, related to the application of piezoelectric material, in my opinion, the bias is more directed to the sensor itself rather than the energy harvesting material, because the matter of efficiency and the cost of the power density related to energy harvesting is slightly few or slightly lower in value of the harvested energy, and the higher in cost compared to some traditional ways, for example, like solar panels, for example. So this one could have or could make an advantage to the part of sensors and transducer compared to this one, to the energy harvesting. Another one, another question related to the piezoelectric materials and why they are lesser in applications and not widespread yet. Again, it depends on the application itself, because the applications like smart textile or wearable electronics, this is the future for different applications and automated health monitoring and so on. But again, this part or this application generally is still not yet developed 100% in our present time. So most likely, whenever we will move further to the automated level or the fifth generation of the industrial revolution, then we will have more work related to that. These materials, the PVDF is, yes, in some development, it becomes very competitive as sensing or actuating materials compared to other commercial-wise materials. But it depends on the treatment. As I said, you need to improve its efficiency by different additives. And yes, it would be competitive with other materials. Of course, as shown here in this last slide, that I'm a supervisor of 2 research labs and research schools, whatever, one in Alexandria University and one here in Kuwait College of Science and Technology. We have different research interests, not only in the nanofibers membranes and its applications in energy harvesting. We have other interests related to optical nanosensors, solar cells, cyber physical system, and much more. And we have good international collaboration network of collaborators worldwide. And of course, if any of you, any professor of your university would like to initiate some collaboration with us, we are welcome to do that. And again, thank you a lot for your attention, and I'm ready for any further questions if found. Thank you.
Thank you so much, sir, for such nice and wonderful presentation. You included some really interesting examples of applications of piezoelectric materials. I hope our participants, they really got some interesting information about these materials, their characterization, and the latest applications. Now, I ask participants, if you have any question, you can unmute yourself and ask your question directly to Professor Nader Shehata. If you have any question, you can unmute yourself directly. I guess all the questions have been answered, sir, because already there were questions in the chat box.
Yes.
Thank you so much, sir, for such nice presentation and wonderful talk.
Thank you. Thanks a lot for having me here. Thank you.
It's been an honor to have you here. Now I declare the end of this technical session here. Thank you so much, everyone, for joining. Thank you so much.
Thank you.
For the next lecture, we'll meet on the 14th of November. Now I'm sharing the feedback link here in the chat box. You can directly fill up the feedback form here. Apart from this feedback link will also be shared on the mails. I request all the participants to please fill the feedback form. The link has been already shared in the chat box.